So let's finish the details of this Ramsey construction. So what we want to prove is this construction showing that this is by Mathis and Vastrat, that the Ramsey number of K4 versus KT is at least up to some polylog factor T cube. Okay. T cube, what's the polylog factor? Over log Q log T to the 4. There's some constant in the front. Okay, so this is what we're trying to prove. And the idea is this random block idea is this random I thought I copy paste here. Okay, so let's see this idea. Let me copy paste. So it's again, you start with something that's highly structured, and then you do some random construction combined with this structured initial graph. And we've seen this also in this early 4-3 problem. So we start with this graph HQ, which has the property that it has roughly Q to the 4 vertices, and it's a regular graph. Every vertex has degree roughly Q to the power 3. And it's very structured in the following sense. It has these two properties that the edge set of the graph, HQ, is actually consisting of edge disjoint union of cliques, maximal cliques, in fact, roughly Q cube of them. And each clique is of size Q squared. So each one of these is KQ squared. There are Q cube of them. They're pairwise sharing exactly one vertex. I think sharing exactly one vertex. Now, the second property, this is already highly structured because the edge sets, they are clustered into these small cliques. The second property is that every K4 in this graph HQ must always contain 3 vertices that lying in one of these cliques. Okay? Now, if we have this last property, how do we modify the graph to make it K4 free? That's our goal. We need to have a K4 free graph of large order without large independent sets. Okay. To kill all K4, then what we do is for this clique, we know every K4 has 3 vertices lying in some clique. If we make it bipartite instead of a complete graph, then every clique becomes a graph that's triangle free in particular. If it's triangle free, then because of this last property, the resulting graph is K4 free. This is what random block construction is doing in the second step. For every one of these cliques CI, you uniformly random partition the vertex into 2 parts, and then you add all the edges going across. Now we get call this graph HQ star, and it's K4 free. But now the problem is it is K4 free, and the graph has order Q to the 4, but obviously there's a Q square independent set here because each clique is of size Q squared. So this independent set is roughly square root n if this is our n, which is too large. We want it to be n to the 1/3. So we're going to do a random sampling to sample vertices with probability roughly 1/q to drop the order down to Q cube. Okay. But then we will show that the independence number actually will also drop by a factor of Q. Okay, this is through this Kleiman-Winston's graph container to count number of independent sets much larger than Q to achieve that. So now let's see the details. How do we get the first step? Okay, how do we get such a graph HQ with all these nice property? So let's start with recalling the definition of projective plane, the finite projective plane. Denoted by of order, let's say K is PG to K. This is the notation. This is basically, this finite projective plane is nothing but a collection of points and lines. So it consists of a set, consists of two things. A set P of K squared plus K plus 1 points, and a set L, which is K squared plus K plus 1 lines, such that it has the property that every 2 points determines a line, meaning that there is a unique line going through every 2 points. So adding 2 points, is this a unique line? Here, is this a unique line going through them? And vice versa. For every 2 lines, they intersect at exactly 1 point. For any 2 lines, their L and L prime, L intersect L prime is 1. And this intersection, I mean, it's intersect at the point in P. Okay? Some point and line structure. There's one example we all familiar. This example is a Fano plane. So Fano plane is a projected plane of order k equal to 2 here. You have 7 points and 7 lines. Okay, it looks like this. So the 7 lines are, you have these outer lines, 1, 2, 3, and you have these cross lines. Let's say here, here, here. This is the 7th point in the middle, and you have one more line that goes like this. Okay. This is the final plane. So in general, there are arbitrarily large projective planes. We're gonna make use of such structure, but we're not gonna work directly with projective plane. We will work with a subset of the points and some subset of lines. So let's try to first view the incidence graph of this projective plane. I think that will be useful. So how do we view the incidence graph? Let's look at the point line incidence graph. This is simple. This is just a bipartite graph where one partite set is the point set P, and the other partite set is the line set L. So you have, in particular, k squared plus k vertices here, and k squared plus k plus 1 vertices here on the right. Same number of vertices on each side. A point is adjacent to a line on the right if it lies on that line. Okay? From this property, it's not hard to derive by some double counting from these two properties that every point actually lies in k+1 lines. So every point in k+1 and vice versa. Every line contains k+1 points. What does it mean in this graph? In this graph, that just means the graph is k+1 regular, right? The degree of a vertex in the point set is the number of lines containing these points, which is k+1. The degree of a line in the line set is the number of points on this line, which is k+1. Okay? And what's another property of this incidence graph from these two? Can anyone tell me? Every 2 points, there exists a unique line going through them. And every 2 lines, there exists a unique intersection point. This implies C4 free of the incidence graph. So this property implies that the incidence graph is C4 free. Okay, why is that? If you have a C4, that would have mean what? P and P prime has 2 neighbor L and L prime. What does that mean? That means for this 2 point P and P prime, there are 2 lines, 2 different lines going through these pair of points. And that's not a property we know. Good. So this is the point line incidence graph. And our HQ, let me first tell you, it will be we will take a subset of point sets here, and we will take a subset of lines here. And you look at this graph. Then we will take the neighborhood clique graph of this graph. That will be our HQ. So let me first define what is U and what is S. So this U also, let's take it for granted, these properties coming from finite geometry. It's called unital. So the definition, the unital U, which is basically a set of points, a set of exactly Q. Now we're working with, I forgot to say, now we're going to work with the order of the projected plane to be Q squared. So in the projected plane PG 2Q squared. So K equal to Q squared. Okay. A unital is a subset of points of P. So now when K is Q squared, how many points? K squared roughly, which is K to the 4. Okay, so in total number of points and total number of lines is roughly K to the 4, Q to the 4. So a unital is a set of Q to the 3 number of points. Is a set of Q to the 3 plus 1 points, such that it satisfies the following property, such that for every line, in our projected plane, it intersects at this unital previously. Let me draw this picture. Let me draw this picture again. So this is L, this is P, and inside we have some subset of points, unitals. Oh, let me draw in the middle. This is our U. Okay, unito, q to the 3 points plus 1. Every line previously, what's the degree? The degree previously is like k plus 1 order, right? K plus 1 is q squared plus 1. So every line contains q squared plus 1 points. But if you look at its every line's intersection with the unito, it contains either 1 point of the unito, exactly 1 point, or q plus 1 point. So it's like 1 or square root of this order equals to either 1. For such line, we call it a tangent line. It's tangent to the unito because intersect at the 1 point. Or q plus 1 points. For such line, we call it secant line. Okay. Now, so that means we have two type of lines. Here is our tangent lines T, and up here is our secant lines, let's call it S. So for every line here, you only have degree 1 to U. That's what it means. And you have degree q squared outside. And for every point here, which is a secant line, it has q plus 1 points inside the unito. Okay. This is tangent. Good. And now we're going to focus on, let's focus on the induced bipartite graph between U, the set of unito points, which is q to the 3 plus 1 points, and the set of all secant lines, all the secants, and look at the bipartite graph between them. Obviously, this is still C4-free because it's a subgraph of the original one. Okay. Let's first estimate what's the number of vertices on the right. How many secant lines are there? So through this through this property of the unito, we know the size of the unito, and we know every line intersect a unito either 1 point or q plus 1. From this, it's not hard to derive that for every point in the unito, let me draw a picture. So suppose this is our unito. Oops. Let me do it like this. So this is our unito U. For every point here, let's call it X. We can see that, I'll leave an exercise for you, that for every point in the unito, there exists exactly one line, one tangent line through X. So there's one tangent line that looks like this, intersecting at U at exactly at X. How many lines going through a point X in the whole projective plane? The number of lines going through any points in the whole projective plane is the order plus 1. Here our order is q squared. So the number of lines going through X is q squared plus 1. We know that there is a line that's tangent. The remaining q squared lines actually are all secant lines going through X. And there are remaining, and then the other q squared lines through X are 6 secant lines. So it looks like this. Okay, and these are points of view. So the points of view in this unito are nicely clustered together, right? How many points here? Each line has k plus 1 points. K is q squared. So remove x. So apart from x, there are q squared points here. Oh, sorry. Q squared points in total on this line. But remember, for secant lines, it intersect at u, the unit of q plus 1. So there are q points actually. Q are the points here. And how many lines in total? Secants, q squared secants through x, right? Now we can do double counting. So the number of secants, which is the cardinality of S, all secant lines, equals to, for every point, we have q squared through every point in U, right? This q squared through x, and this is true for every x, q squared of them. But now we overcount it. Oh, sorry, for every point. And how many points we have? You need to multiply by the cardinality of U, right? Here, the cardinality of U is q cubed plus 1, number of unit points. But we overcounted. Why? Because if you look at this point, and this is also a secant through this point, right? So this is every secant is counted exactly q plus 1 times. That's the size of the secant intersection with U. So we need to divide it by q plus 1. Divided by q plus 1. Size of L intersect U, overcounting factor. Okay, and you get q squared minus q plus 1. It's again roughly q to the 4 lines. So the number of secant lines is still roughly almost all lines, q to the 4, but the number of unit points is q to the 3. It's a lower order. So this is, we can write it here now, q squared minus q plus 1 lines. Good. So, any questions so far? The key property of this, now we are looking at this space, right? The key property of this space is that no matter how you take 4 secant lines, you cannot find 6 unit points where these 4 points meet at these 6 points. In other words, you don't have 4 lines in general position. So a key property of U and S. Okay? No, this is so-called O-none, or another name is Pusch configuration. This is nothing but just 4 lines in general position. Okay. So you cannot find 4 lines which are 4 secants, i.e. 4 lines in S, 4 secant lines meeting at 6 points in the unit of U. Here, every 2 line determines a point, right? 6 points. So this is the O-none path curve. We don't have this. Now let's see what this means in the point line incidence graph. What does this is equivalent of saying in point line incidence graph of U and S. Remember, this is our U, which is subset of P. And now we take secants not all the lines. This graph has no 4 lines here. These are the 4 vertices on the right, right? Such that they meet at 6 points. What does it mean meeting at 6 points? Let's look at this line. Let's take this guy, which is this guy, and this guy. Let's take this one. Why not? Right? Meeting at this point. So in the incidence graph, that means these 2 red and green points on the right, they have a common neighbor, which is a yellow neighbor in U, right? And this is, if you have such configuration, this is true for every 2 lines, for every pair of these points. And for every pair of this point, you have unique intersection points in U. This is exactly a 1 subdivision of K4 with 4 vertices in the S. So i.e., no 1 subdivision of K4 with 4 vertices on the right. I vaguely remember you don't have. What about K4 subdivision with 4 vertices on the left? Okay, I'll leave it for you to check. So here we know that there's no 1 subdivision K4 with 4 the 4 core vertices lying in S. Okay, now we can define our graph HQ. Our graph HQ takes vertex set. So our graph HQ takes vertex set S. The vertex set is S, the set of all secant lines. Okay, and what's the edge set? For the edge set, the edge set means this is our vertex set. So the vertices are lines. So 2 lines are adjacent, L and L prime, if their unique intersection points lies in U. Remember, these 2 lines, they lies in the projected plane. They definitely has a unique intersection point, but this point could lie in P, right? Somewhere outside of U. If these 2 secant, their intersection lies in here, I put an edge. If their intersection is out, I don't put an edge. Okay? So here, put an edge. Let me draw a different picture maybe. So this is P. This is U. Now we cared about S here. For every 2, if their intersection point is here, I add an edge. And if, for example, you have 2 here, their intersection points outside of U, unique one, I don't put an edge. Okay. Any question about, this is the definition of HQ. That's it. Now we're going to prove we're going to translate all this previous property of unitos and secants into property of this HQ. That will be the properties that we listed last time. Any questions so far about the definition? Okay, let's first, I forgot to mention this, again, I find it useful to look at this incidence graph here between unitos and secants. So let's draw this graph. So we have U here, you have seconds here. You have q squared minus q plus 1 seconds. And we have q plus 1 points lying in the unital. This is a biregular graph. Biregular means all the degree here are the same, and all the degree from the other side is also the same. What's the degree from this side? As I said, it's q squared. Every line, there are q squared seconds through every point in the unital, right? So it's q squared degree from the left. What's the degree from the right? Degree from the right is for every secant line, how many points, unital points lie on the line. That's q plus 1. Q here plus x itself. So this is q squared, q plus 1 biregular. Q squared, q plus 1. And it's easy to check this thing, it adds up if you count the edges. Now, how do we view HQ in a different way? View HQ in a different way, equivalent way actually, is that this graph is basically saying we look at the incidence graph. You look at the incidence graph of U and S. Now, for every point X in U, you plant a clique in its neighborhood in S, right? Because whenever two lines, their co-neighbor lies in U, unique co-neighbor lies in U, they are adjacent. So in particular, if you look at the neighborhood of X inside the secant, all the points here, they should be pairwise adjacent. They form a clique. So every vertex, its neighborhood is a clique. Furthermore, because it's C4 free, every 2 points determine a unique line. These cliques are pairwise sharing exactly 1 point. There's a unique line going through these two right points. So sharing, they are edge destroying also. They are edge destroying also. So let me write it down. HQ is the same as the edge set of HQ is the same as the union of edge destroying cliques KQ squared. This neighborhood is KQ squared. So if this is X, this is clique CX. Okay. Index by points in the unital U. Does it make sense? Right? So we've just proved that, and the number of, it's actually you can show that this is maximal clique. This number of maximal clique equals to size of U, indexed by points in U, so it's QQ plus 1. That's one of the properties we mentioned about HQ. Now, so let's list the properties of HQ. This is a lemma. So HQ is an n-vertex d-regular graph where so this is first property. HQ is an n-vertex d-regular graph where n equals to the number of secant lines. Oops. The number of secant lines, which is this guy. So number of vertices q squared minus q plus 1. What's degree? I will leave it for you to write out details. The degree is easy. You need to look degrees. You have a line here. you look at the neighbors, right? What are the other lines, the vertices that it's adjacent to? You first go back to a point in the unitole that this line contains. Now, everything lies in the neighborhood of this point x is adjacent to x. It's a clique. So you have q squared minus 1 points inside this clique, apart from L itself, right? And how many in this point x? The point x, you have q plus 1 unitole points lying in x. This is number of choice. And at every such point, this clique is edge disjoint and share exactly one vertex. This vertex is L. So you have another q squared minus 1 for all the other choices. So the degree is q plus 1 points q squared minus 1. Okay. Right. So this is roughly q cubed regular. Let me write down the proof. This is number of unitole points in L, in any line L. And then for any such points, x in L, neighborhood of x, intercept S. Is q squared. Then you have to minus the line itself. That's q squared minus 1. Good. The third property, the second property is that that I have already mentioned here, but let me write it down formally. The edge set of HQ is the union of Q cube edge disjoint maximal cliques KQ square pairwise sharing exactly one vertex. Okay, this is also not hard, deriving from all those previous properties. So in particular, this is derived from C4 freeness, right? Of the incidence graph. In other words, 2 points determines a line, 2 lines determines a point. The third property is that every the third property is every vertex in this graph, which is a secant line, remember, is in exactly q plus 1 cliques, such cliques, such maximum cliques. Why is that true? That's how we count this degree, right? Every line here, secant line, inside this Cx is inside all the, you look at all the points, x prime, look at their neighborhood. It also contains this line. So it's exactly q plus 1. Okay, here the proof, let me write down just for complete sake. So let's say this is L in S, right? And if we index this edge disjoint, let's call it C, collection of edge disjoint maximum KQ, which is Cx, where it's indexed by the points in the unitole. Okay, and this is nothing but the neighborhood of x intercept at S secant lines. This neighborhood you make into a clique. Now, for every such thing, for every secant line, the number of cliques containing this line is exactly this is exactly Cx, where x lies in L. Okay, easy. The last property, which is the important property, every K4 in HQ contains at least 3 vertices in some Cx in C. This one of this maximal clique in the collection. This is also easy. Well, we assume there's no O-non configuration. Remember, we don't have, first of all, what does a clique mean? A clique means maximal clique in HQ. First of all, clique in HQ, what are the vertices in HQ? Are the lines, right? And vertices are pairwise adjacent, means they pairwise intersect at the point in the unitole. So a maximal clique is actually this picture that I drew already here. Is this concurrent is the same as this Q square every such clique is a collection of concurrent sequence. Concurrent just means these lines, they all share a, concurrent just, this means concurrent, okay? All the lines share one exact common point. So here's the common point, right? This is what it means geometrically. So we know that, what do we know? We know that there's no 4 lines in general position. We know that for every 4 secant lines, this is no. What does it mean 4 lines not in general position? That means there must exist at least 3 of them sharing one common point. There must exist 3 concurrent lines among all 4 secant lines, right? This implies there exist at least 3 concurrent lines, concurrent secant lines. And what does these 3 concurrent sequence means? This just means the same as I mentioned here. It means a triangle in HQ. Concurrent lines means a clique. So 3 concurrent lines means a triangle. At least, this implies at least 3 vertices inside this clique CX, which is their common point, right? That finishes the last property. Good. Any questions so far? Let me give you some additional property of HQ, which we will not use throughout the proof, but it could be useful for other problems. Actually, HQ is a strongly regular graph. So HQ is a strongly regular graph. In spectrum graph theory, people care a lot about strongly regular graph. We've seen that this graph is a regular graph, meaning that every vertex has degree was q plus 1 times q squared minus 1. But in fact, it has stronger regularity. For every strongly regular graph means apart from the graph being regular, you require every adjacent pair of vertices have the same codegree, and every non-adjacent pair of vertices also have the same codegree. So the property that also, For every adjacent pair of vertices, UV, their codegree is the same, which is 2q squared minus 2. And for every non-adjacent pair of vertices, their codegree is also the same, can be computed, which is q plus 1 squared. Okay, strongly regular. And in the spectral graph theory, the spectral information of strongly regular graphs are known. So spectral info of strongly regular graphs, SRG, strongly regular graphs are known. In particular, we know that lambda 1, the largest eigenvalue, just the regularity D, and the non-trivial eigenvalue, lambda 2, the second largest one, is q squared minus q minus 2. The multiplicity is q cubed. The smallest eigenvalue is negative q plus 1. Multiplicity is q squared minus q minus 1. Q squared plus q minus, minus q plus 1. We will not use this here, but could be useful elsewhere. Let me just throw it here. Now, that's the first step. We have now our HQ. We know how it looks like. In HQ star, our second step in the construction, we go from HQ to HQ star. This is the random block construction, if you recall last time. Okay, it's also very simple. It basically just means this is your HQ, right? Now instead, we HQ star is you randomly partition these into bipartite graphs and put the complete bipartite graph in there. This is random block construction. A key property we use there is sort of pseudo-randomness, locally denseness. Here's the theorem. For every Q large enough, this is pseudo-randomness, locally denseness. Pseudo-random, locally dense. For every large Q, there exists a K4 free HQ. This is a random graph after all. So we can show that with high probability, one of the outcome HQ star, which is K4 free, it satisfies this local denseness condition. How many vertices with H squared or Q squared minus Q plus 1 vertices, such that for every set X of at least M equal to 2 to the 20, roughly Q squared points, vertices, we have the number of edges induced on X is at least X squared over some constant, doesn't matter, over Q. So I mentioned last time, remark, both this density Q and the threshold M is optimal. Both M and density 1 over Q optimal. This is optimal because obviously there's a independent set of size Q squared. This is optimal because even HQ has density 1 over Q. D over N, right? Which is 1 over Q, roughly. Good. Now I want to mention okay. Good. So let's finish the rest of the details. This I will not prove it, this theorem. It's some you use some concentration inequalities. I'll let for you to fill in the details. So let's finish from here. How do we go to bound, to do random sampling to a induced subgraph of HQ star to get a final graph? That's the last step. So here's what we add after the second step. Now, in the last step, first of all, we start with this graph from second step. Maybe there's some property I need to prove about this graph, HQ star. So a lemma is here. Property of this HQ star, what do we know? It's K4 free, locally dense. So the locally denseness local denseness or locally denseness, locally dense, local dense, local denseness. In front of the verb, now it should be adjective, right? So it's probably local denseness. So from the local denseness, using Kleiman-Winston's container, we can derive the following property of HQ. The property is that if we set T to be roughly Q log Q square, then the number of independent sets, this means the number of independent sets of size T is at most Q over log Q square T. Okay? For this calculation details, I will refer to the paper. Some calculations. So I will skip this part. It's pure calculation, not very interesting. So we can bound the number of independent set of size T through this container method. How do we do random sampling? We want to, it's already K4 free, but we want to reduce the independence number from Q square to T. Okay, we would like to reduce from Q square to T. How do we do that? You want to have, after sparsening, the expecting number of T size independent set drop below 1 in expectation. Then that means there exists the outcome with no size T independent set at all. And how do we go drop below 1? For every this fixed size T independent set, the probability that it survives after sampling is exactly P to the T, because every vertex is chosen with the probability P. And there are T vertices in this independent set. They all survive after this random sampling is P to the T. So you want these to be less than 1. That means P needs to be smaller than the reciprocal of that. And let's take P to be that. So take Now the third step is random sampling or sparsening to reduce independence number from Q squared down to T. So how do we do that? You take probability P equals to, what is P? Log square Q over Q, exactly the reciprocal of that. Then this implies the expect, and then take P random subgraph of HQ star, meaning every vertex is chosen with probability P independence of others. Look at the induced subgraph. Now the expected number of independent sets of size T, let's call the final graph G. In G is at most number is independent set is at most this times P to the T, right? Which is 1. So that means there exists okay. So this means the expected, let's look at the expected value of number of vertices in G minus this quantity. So this is then at least number of vertices exactly P times N, right? Minus expectation is at most 1, we computed. So we know what is N. N is roughly Q to the 4, roughly Q to the 4, divided by, multiplied by P, so it's roughly Q cubed log Q squared minus 1, that's divided by a factor of 2, is at least Q cubed log Q squared divided by 2, okay? So that means there exists an outcome of G where this is bigger than that. So we can remove a vertex from every independent set of size T from G, and you obtain the graph which has no independent set of size T on this many vertices. So there exists a graph, a choice of G such that we get alpha of G is less than T, and number of vertices bigger than Q cubed log Q squared over 2. Okay, this is also simple first moment dilation. This is it. We are done. Number of vertices is roughly Q cubed. This will be our N. And this T is what? T is Q log Q squared. So rough is Q. Q is 1/3, N to the 1/3, roughly. Okay. So two remark here I have. The first remark is this conjecture that I mentioned last time. remember the conjecture by them is saying that the Ramsey number for T, it should be big theta. So they prove T cubed over log T to the power 4. They conjecture that it should be log T to square. And to prove this, the obstruction is in the container lemma bounding the number of independent set of size T. So the obstruction remark, so they believe probably we need to show, is it true that, so here, we take T to be roughly Q log Q squared, right? And this is Q squared over T, roughly some constant to the T. Yeah? We want to get a better estimate on the number of independent sets, same estimate, but for slightly smaller. If you can bound a number of independent set of size T, where T is Q log Q, not log Q squared, and prove the same bound, we will be done. You can prove this tight bound. That will be a very good result, I think. So it is true that the number of independent of size T is at most CQ squared over T to the power T here. Okay. In this HQ star. For T to be big O of Q log Q. This will be enough to prove this. And the problematic part is obstruction. Is the container part. Lyman-Winston container part. We need this extra log factor argument requires an extra log factor. Okay, that's the first remark. The second remark is about, again, this part. In this part, we use container method to bound the number of independent sets. And that's so far sort of the only way we can bound the independent sets. Because in HQ star, the minimum eigenvalue is not good enough to employ these spectral methods. Remember, when the minimum eigenvalue is large, then we can use spectral methods. Here, HQ is quite good. For HQ, the minimum eigenvalue is roughly negative Q order. But when we pass to HQ star, the minimum eigenvalue becomes at most negative Q squared because of this random, because of this bi-click complete bipartite graph of order Q squared by Cauchy interlacing. So this eigenvalue is not good enough for us to apply this spectrum method. Nonetheless, I would like to mention this spectrum method to bound the independent sets. This is a result of when we have strong spectrum bounds, we can also bound number of independent sets. So this is Alon Rerdel in their paper for multicolor Ramsey number. They prove that for every ND lambda graph where ND lambda graph means it's an n vertex graph that's D regular. And the absolute value of this non-trivial eigenvalues is at most lambda. So for every maybe let me, before I mention this, I want to mention some simple observation. So first of all, let's say we want to bound. Say we want to bound independent sets in n vertex D regular graphs. Okay, if we set T to be n over 2D plus 1, roughly average size, roughly the size of independence that you get from greedy algorithm. From greedy algorithm, you pick a vertex, you kick out its D neighbors. Every time you kick out D plus 1, you get roughly this size, right? So the number of independent sets of size T is at least in such graph. You have n choices for the first vertex of independent sets. After you choose the first one, kick out its neighbors, n minus D minus 1 for the second one, n minus 2 times D minus 1 for the n minus T minus 1, D plus 1 for the last vertex, right? And this choice, you might choose them in any arbitrary order. You divide it by T factorial. This number, by our choice of T, is at least n over 2T to the T, right? T to the T is just T factorial. N over 2 is this. Every one of these is bigger than n over 2 because of that. This multiply that is at most n over 2, okay? And what is that? In particular, n over 2T is roughly D. So it's D to the T. D plus 1 to the T. So in any n vertex D regular graph, if you look at independent sets roughly the greedy size, there are D to the T for this T. But if you look for something slightly larger, there are much fewer ones. That's what Alon and Rudolph showed. However, surprisingly, if we look for slightly larger independent sets, there are much fewer in ND lambda graphs, this sort of pseudo-random graph. So let's recall, this is n vertex D regular, and the maximum of lambda 2, lambda n eigenvalue maximum is lambda. So all the non-trivial one, apart from the first lambda 1 equal to D, is at most lambda in absolute value. Their result says, in such ND lambda graph, if you set T to be some constant n over D log D squared, you see, we go a little bit larger than the greedy size. So this is the greedy size, a little bit larger. Then the number of, maybe there's a constant here, check. Number of independent sets of size T in such ND lambda graph is at most the eigenvalue over log 2 minus little 1 n raised to power t. Okay, and why is this good? Look, for the greedy size, n over d, you get d to the t. And now for n over d, just log d square above, slightly above. It drop all, this is, if you think of this as low order term, is lambda to the t instead of d to the t. And for many pseudo-random graph, lambda and d, lambda is polynomially smaller than d. In our graph HQ, right? D is roughly QQ, but lambda for HQ is Q squared. It's polynomially smaller. So you get much fewer or slightly larger. Okay, there's some related results that could be useful elsewhere. Sometimes if you have the spectrum information, you don't need to prove supersaturation and then use Kleiman-Winston's container. You can directly use this bound to bound the number of independent sets. Any question? Okay. So now let me also briefly mention this multicolor version that they proved. They also proved that this is the R K4, K4, dot, 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 K4, and then KT. Okay, this notation is R K4 T. Total number of colors is K. So there's K minus 1 colors in K4 and the last color in KT. I think last time I used K here, but doesn't matter. You just shift the parameter. So this, they prove that is big theta of T to the 2K minus 1. Okay, so how do you prove this? The idea is from this Alon-Rerdel paper that I mentioned. Basically, let me briefly mention how they do that. You take this K4 Ramsey graph, and then you take its blow up. Now you take random overlap of K minus 1 copy of them together, and that's it. That's the idea. Idea is take random overlaps of blow-ups of this K4 Ramsey graph. This is one sentence summarize of their idea. Slightly more details. How do they do that? Okay. Start with T vertex graph. G, I think they call G little t. Maybe just call it G, which is K4 free. And the independence number of G is roughly T to the 1/3, right? This is the K4 Ramsey graph. When I say roughly, I just means up to log factor, T to the 1/3. Now we take a blow up of it. The size now blow up size R, where you take R to be some polylog vector up again to some polylog vector T to the 2K minus 2. Okay, so let's call this you get this G blow up to R. This just means for every edge, every vertex blow up to a size R independent set. And every edge becomes KRR. All right? You blow it up. Now, that's the first thing to blow up. Oh, here. What does this mean? Well, first of all, the property of this graph. Alon and Rödl proved that for such blow up, GR, what's the number of vertices? Number of vertices is T times R, right? You have T vertices blow up to R, and they bound the number of independent sets of size T. Roughly this guy. Oops. Let me write this. Little t. Let me call it S. Which is roughly t to the 1/3. That's the independent set of the original graph. If you blow it up, and now you count independent sets that's slightly larger than the independence number of the original graph, number of independent sets of size S log X, basically. T, where now let me take T, set T to be S log X, slightly larger than the independence number. We can bound this number of independence number, independent set of size T is at most this quantity, some quantity M, okay? They can bound it. I can write it here if you want to see it. I will not prove this one. T factorial. Okay, there's some number. You can bound it. Now, let's go to the overlapping parts. This is the first step. Second step, random overlap. What does it mean? We now going to take k-1 copies of this guy, blow up. Take k-1 copies, call it G1, G2, GK-1 of this blow up, GR. Now, look here. For all these copies, we're going to randomly permute its vertices and then put them on the same vertex sets. In other words, you have G1 here, right? Now your G2 just randomly permute the vertices, put it on top of G1. G3 randomly permute its vertices, put it on top of the previous two, and so on and so forth. You kind of randomly permute the vertices, put them all to take the union of their edge sets. Independently take a random ordering permutation of their vertices. On the same vertex set and take their union. Okay. That's the resulting set. Let me call it G. Oh, I use G, right? The final set, final graph. Let me call it G star. Is the union of, yeah, let me not write. Okay, this is the union. Now, this is what we want. One of the good choice is what we want. How do we see it? First of all, for this graph, you can give a k-1 coloring. You just look at the edges of G star. which graph it belongs to. You give that color. Sometimes an edge could belong to 2. You just give an arbitrary one. Each one of this color is obviously K4 free because the initial GI is a copy of this blow up, which is K4 free, right? So G star come with a natural coloring, edge coloring. Basically, E, depending on E belongs to which GI, you give color I. Okay. And this implies K4 free for the first K-1 colors. You just need to prove left to show, suffices to show with positive probability alpha of G star. Now we need to control the last color, which is the complement of G star. That's the last color. It's independence number, the clique number there, which is independence number of this guy. You want to bound this to be at most T, actually, we will show. Okay, and we know this. The number of independent sets of size T is at most M. Okay, so what do? This G star is a random overlap of K-1 copies. Now, we need to estimate, fix a set of vertices T, a set of T vertices in G star. Fix a T set in V of G star. Now let's estimate what's the probability that it form an independent set in G star. Let's call this set X. The probability that X is an independent set in G star is what? Is at most, I claim, M over R T choose T. Why is this true? Look. Total number of choices of T sets is the number of vertices of G star choose T, right? What's the number of vertices of G star? Is T times R. So this is the total number of T sets. And among these T sets, because we randomly permute the vertices, put it on top of vertex sets. M of the T sets, they are independent sets. We bound the number of independent sets of size T in each copy of GI. There are at most M of them. So the probability that this T set will be the target set of this one of these M set, independent sets. Probability that M of such sets land on this particular X is M over total number of T sets. Now use linearity of expectation. So the expected number, this implies expected number of independent set of size T in G star is what? Is at most sorry, I forgot the factor. You need to raise to factor K minus 1. Why? This is independent in G1, in each GI with probability this. And we take independent permutation of each GI. There are K minus 1 copy of them. So X is independent. It has to be independent in every GI. So this is probability that X is independent in GI or any I in K minus 1. And to be independent in G star, X has to be independent in every GI. So you need to take the products. They are independent, K minus 1. So now this is at most total number of T sets R T, choose T, times this number to the power K minus 1. And by our choice, this will be strictly less than 1. That's how we set up the parameter. And that would imply that G star is the thing we want, right? So recall, number of vertices, G star is R times T, which is roughly what? T to the 2K minus 1. And alpha of G star is less than T. This implies the thing we want. Up to a polylog vector, T to the 2K minus 1. Okay? Any questions? Right. So it's about time. So we finished this one. Good. So next time I will mention a couple of more remarks and one more example of this random block construction in a closely related problem to the Ramsey problem, so-called Erdős-Roger function. Then we move on to other constructions next week. Right. Thanks for listening. See you guys next week.